All right, next stop we will talk about to express Kc when an equilibrium contains liquid. Okay, that's basically solvent. So in this case, we have acetic acid, an acid, right? Dissociate in water, making hydronium ion and acetate ion, right? So we use Ka or Kc, same thing. So acetic acid is an acid, so we use Ka or Kc, same thing there. To express same thing, the concentration of product over concentration of reactant, you know? And now, here what happened though, when the reactions keep going, proceed forward, right? Making a product, come back to the reactant in equilibrium. Does the concentration of water, which is a solvent, change? Interesting. Is it change? Well, solvent is the majority of the component in the solution, so the concentration doesn't change. Actually, the concentration of water is about 55.5 molar, right, at 25 degrees Celsius. And the concentration of water stay the same, never change. There are a lot of them, all right? So what happened is the concentration of water is a constant. If it's a constant, here's what I'm going to do. So I'm going to move the water right here to the other side by times water on both sides. So water cancels out on the right. So I have water right here. So we have a constant times Kc, which is also a constant, right? So we write a new constant Ka. That's why in acid we use Ka. That makes sense. So Ka of an acid equal to the concentration of reactant over the product, and ignore the liquid phase, which is gonna its concentration stay the same, right? So my point is, when you see a liquid, don't include the liquid or solid compound in the equilibrium equation. For the solid compound, same thing. The concentration of solid doesn't change. I'll take a look here. So calcium carbonate, solid, that decomposes over time to make calcium oxide and carbon dioxide gas. All right, to write Kc right here, well, easy, regular Kc. So the product over reactant, so I include everything, okay? But the concentration of solid never change. Calcium carbonate is still calcium carbonate, not do anything, right? Calcium oxide also solid. So these two are constant, you know? So I'm moving calcium carbonate to the left side, to the top, calcium oxide to the bottom, look like that. And I rewrite the new equation. That's a Kc, and Kc is equal to just the concentration of carbon dioxide. That's it, right? If you don't believe me, let's take a look here. So to experiment, right? So on the left side, so this same reaction go right here. So we're doing right here. So calcium carbonate to making calcium oxide and carbon dioxide. Then they are in equilibrium, all right? So on the left side, they are more calcium carbonate. Like you see the orange, those are calcium carbonate. Same amount of carbon dioxide. If you see the pressure of carbon dioxide, that's level. Right? On the right side, they are more calcium oxide. Now they are more, so we add more calcium oxide. The pressure of carbon dioxide that never change. There's nothing changing here. All right? The pressure of this is manometer. So the level of mercury is still the same level, which means that the pressure of carbon dioxide is still the same. So equilibrium doesn't change when add more solid. Basically, the concentration of calcium carbonate, calcium oxide, which is a solid, never changes. So my point is, when you see a solid or liquid phase in equilibrium, just ignore it when you want to express the equilibrium constant. Okay, all right, let's try this. Write the equilibrium equation for the auto ionization of water. Now take a look. KD, D stand for dissociation. So these two combine, dissociate to hydronium ion and hydroxide ion. Okay, so same thing, just act like a K, like the Kc, same thing there. This is the constant. What I'm gonna say. This is the dissociation of water, so we use Kw. The equilibrium of water, so we use Kw. Same thing with Kc. Okay. If you ignore the liquid phase, so all of Kc that you have is just concentration of the product times concentration of hydroxide ion. So these two combined. That's it. And if you want to combine, if you want to see the whole thing, I'll show you. So do like normal. So product over reactant. So there's a product over reactant. So there are two waters, so water squared. but water concentration of water never changed. Say always 55.5 molar at 25 degrees. That's so that this is a constant. So I move to the left side by times water square on both sides. So water cancel out on the right side, and this is a new constant Kw. We call Kw basically. Okay. All right, try this one on your own. Okay, so magnesium hydroxide is an active blah, 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 blah. What is the value of Kc if solid magnesium hydroxide is dissolved in water and equilibrium concentration are, so we have magnesium that number and hydroxide that number. Okay, so first off, can you write this equation? What's going on here? All right, so magnesium hydroxide dissolved in water and produce magnesium ion and hydroxide ion. Right? So you should be able to write like that. So magnesium hydroxide dissolved, you get one equivalent of magnesium ion and two equivalent of hydroxide ion. Okay, and now Kc. So we have solid here and aqueous and aqueous. So don't include a solid, right? So Kc just the product, no reactant in this case. All right, and then you just plug in 1.65 times 10 to negative 4th. And what hydroxide ion 3.3 times 10 to negative 4th, put in there. Don't forget the square for the hydroxide ion. Do the math there. So coefficient times coefficient, the multiplier with multiplier. So I do it like that, and you should get that number, or 1.80 times 10 to negative 11. Okay. All right, one more time. Let's make sure you get this. When ammonia dissolved in water, it produces small amount of hydroxide ion and ammonium ion. So it is two to the equilibrium below. Write an equilibrium expression for this reaction. All simple there. So we have liquid there. Just ignore it. All right. So this one Kc gonna be. Oh, we use Kb because ammonia is the base. There are a lot of Kb, Ka, Kb, Kw, but those are Kc. Same thing. Okay. Let's see. So the product hydroxide times ammonium ion, right? And the reactant only the ammonia, concentration of ammonia, right? Don't include the solvent. Okay. All right. Same equation. So same thing. So calculate the concentration of hydroxide ion. Right. So we want a concentration of hydroxide ion. We have Kb 1.78 times 10 to negative 5. This guy Kb. And for a solution that is 0.5 molar, so we know the concentration of ammonia and concentration of ammonium ion. All right. So in this case, so we have to move things around. So we want to find the concentration of hydroxide ion. So I'm going to move anything else that's not hydroxide ion to the other side. So ammonia to the top, ammonium to the bottom. Okay. So we got Kb times ammonia over ammonium ion, right, like that. All right, and then let's just plug in Kb. What's Kb? So it's 1.78 times 10 to negative 5. Ammonia, concentration of ammonia 0.500 molar, and ammonium ion 0.00298. There we go. Do the math there. You should get that number 365, 2.99 times 10 to negative 3rd molar. Okay. Now, what is the pH of this solution? We haven't talked about pH yet, but we're going to talk about the pH in the next chapter. So don't worry about it. I'm going to skip that. All right. Let's go to the next video.